All right, quick announcement before we start, that I'll probably send an email about and remind you in class next week as well. So May 4th, which is the very last day that we're scheduled to meet, is we're going to do the teamwork exercise in class. So you have to be here to get the credit for that. So expect close to a full house that day. That will be graded on participation, so more or less show up and don't disrupt the proceedings, and you'll get credit for that. And it's a requirement, as I said, by the university that we assess both teamwork and communication. I did this last year. Seemed like it worked pretty well. So it's just going to be some group work that you'll do, some problems, some thought processes that you're going to kind of go over with each other. So you'll assemble into teams of 4. We'll organize all that on the day. Okay. So make sure you're here for that. The other thing that's happening is, as of, I believe it's tomorrow, the course evaluations open up, which can be completed through May 5th, which is the reading day. I will give time at the beginning of the class on May 4th for people to do that if they haven't yet, to try to encourage greater participation. That also worked well last year, but you can do it on your own time at any point through Access UH, and I certainly appreciate if you take the time to do that. All right, so we're going to start today with leaving off with a couple of problems we didn't finish up last time on phase diagrams. So this will be a good reorientation of what we covered last time. And also recall, this is the last major topic that's going to be on your exam next week. So we had pretty basic phase diagram. There's variations in terms of the temperature scale and the pressure range that they cover, but the type that we expect you to be familiar with have this sort of basic layout. And we just ask you a bunch of questions that you can answer from these diagrams. So in this problem here, we have a researcher starting with a substance at 0.2 atmosphere and 100 Kelvin, increases the pressure to 2 atmospheres while maintaining a constant temperature. Which of the following lists, in the correct order, the phases that will be encountered during this process? So this is the first we've seen where you're considering what happens as you change the conditions of a substance and what phases will be encountered during that process. And so we, again, remember that in these diagrams here, there's 3 regions that are divided up by the lines that are shown. Solid all the way on the left, gas all the way on the right, liquid in the middle. And we're going to figure out, as we move through the process that's being described, what would be the different phases that are encountered. All right, so we go to where we're starting, which is 0.2 atmospheres and 100 Kelvin. So that's right there. That's our starting point. So at the start, we're very clearly in the region that's labeled as gas. So we're below the liquid gas line, below the sublimation line. So we're in the gas phase region. And as the problem says, we're going to just increase the pressure at a constant temperature. So that's going to be, in this case, a vertical ascent through the diagram, because pressure is on the y-axis in these diagrams. So we're going to go straight up from there until we get to 2 atmospheres. So we're going to go like this. Sorry, I can't draw straight, but I'll do better. We're going to follow that line straight up, constant temperature 100 Kelvin, all the way up to, keep going to 2 atmospheres, all the way up to there, okay? So we go all the way to there. Now, as we go through this process, we see that we cross 2 lines. So as we get here to about 0.4 atmospheres, as we raise the pressure, we cross this line here, which takes us from gas to solid, sort of the reverse of sublimation. So we encounter the solid phase once we get to 0.4 atmospheres there. We remain in the solid region, and then right around 1.6 atmospheres there. So there and there are the phase changes marked with X's. At 1.6 atmospheres, we cross from solid over to liquid. So this is another substance where the slope of the solid liquid line is negative, meaning that as you increase the pressure, as you condense the material, you'll eventually cross over from solid to liquid. So we'll reach the liquid phase at 1.6 atmospheres, and we remain there until the end. So that's how we kind of approach a problem like this. So we start with gas, we go to solid, we end with liquid. So the one that is correct would be choice D for this one. Okay, so all three phases are encountered in that particular order when we rise the pressure at this constant temperature of 100 Kelvin. Okay, any questions on this? All right, this one I kind of already hinted at and we talked about a lot last time, which is the relative densities of the solid and liquid phases. We just saw it, what happens in the last problem. So this line here has a negative slope. And when that's the situation, as we saw with the path we just took, at some point, if we're in the liquid region, sorry, we're in the solid region here. We're in the solid region here. At some point, we will cross that line and go to the liquid region, right? We maintain a constant pressure, or sorry, constant temperature. So what that means is as you go to higher pressure, it converts from a solid to liquid whenever that line has a negative slope. And so going to higher pressure is equivalent to compressing the substance, compacting the molecules or atoms closer together. So that means that as the substance becomes more dense, it changes from solid to liquid. So that means liquid has higher density than the solid. All right. And that's really all you can tell from the slope of this line. This is the less common situation, I suppose. This is what water does. Most substances, there'll be a slight positive slope to that line, but whichever direction it goes, you can predict relative densities. Okay. All right, very last one is we want to know what is the vapor pressure of this substance at 250 Kelvin. And so we can kind of go in both directions now. We had a previous problem where we predicted the boiling point at a particular pressure, where you go over horizontally at a specific pressure and figure out where the liquid gas line crosses. So this is solid liquid gas. We're talking about vapor pressure, vaporization, boiling, any of those things. We're talking about the conversion between liquid and gas. Here, though, we're looking for vapor pressure at a specific temperature. So we're going to go to that temperature that's specified, 250 Kelvin, and we're going to figure out at what pressure does the liquid gas line meet at that temperature. So it's right there, just above 1.2. Again, these scales are not usually that precise, so pick the one that's closest if it's multiple choice. But that line here tells us what the vapor pressure is at a given temperature. It also tells us what temperature the substance would boil at a given pressure. It works both ways. So wherever that liquid gas line is going to tell us what the vapor pressure is at a specific temperature. As I said, here it's like just above 1.2, so I'll call it around 1.25 atmospheres to the best that I can estimate it, but somewhere in that range. Okay, so this line here, the liquid gas line, we can use it to predict either the pressure dependence of the boiling point, or conversely, we can predict the temperature dependence of the vapor pressure, which we have equations for, but this allows us to do it graphically without having to do all the math. All right, so any last questions on phase diagrams? All right, so we're going to move into the next part. I will mark here that this is the end of exam 3 material. Pretty clear divide now, because everything we're going to do for the rest of chapter 9 to close out this course is going to be on the solid phase. So just to, again, reorient you, the exam 3 material that's at the beginning of this chapter is all about liquids and phase changes. Now we're going to talk specifically about properties of solid materials, and that's going to all be stuff that's only covered on the final exam. So first we need some definitions to start on. There's sort of two major categories of solids, and then within each of these, especially within the crystalline solids, we're going to break it down further into additional categories. So a lot of this section is going to be categorizing solids on the basis of their structure and how that relates to their properties, which is a lot of what we do in chemistry, is relate structure to properties. But first, there's sort of two broader categories that we want to consider. So there's amorphous solids, which are solids that have no regular structure. So in an amorphous solid, the atoms or molecules that make them up are randomly arranged. They're held together by intermolecular forces, as we've already talked about, but there's no regular way that those are arranged in that solid. They're just kind of randomly piled together. So what it's made up of depends on what type of substance it is, whether it's an element made up of atoms or an ionic compound made up of ions, or there's different types of these substances. But the key thing for amorphous substances is that whatever the building block is that makes them up is going to be just randomly arranged, no regular structure to it. Now, amorphous solids, for that reason, there's not as much we can say about them. So honestly, in this course, we're going to define what they are. I'll give you one example of an amorphous solid, and probably beyond that, we're not going to say much about them, because if they don't have a regular structure, how can we really talk about their structure in a systematic or meaningful way? So that's what amorphous solids are. The classic example of an amorphous solid is glass. So glass is primarily made up of, well, there's different kinds of glass, I suppose. I don't want to say this is universally true, but the most common types of glass are made up mostly of silicon dioxide, SiO2, same material that makes up a lot of sand. But in the glass phase of SiO2, the amorphous phase, as it's called, the silicon and oxygen are just kind of like randomly all arranged. They're all bonded together. There's a little bit of a pattern to it, but there's no regular repeating pattern that you can sort of point to and kind of clearly define what that structure is. So it's very random, and in some ways it's not a perfect analogy, but amorphous solids are kind of like liquids in that regard. They're not flowing like a liquid, but the atoms and molecules also are kind of just randomly piled all over each other and not arranged in a regular pattern. Now, the type we're going to talk about a lot, though, and I think is a very interesting aspect of chemistry in general, are crystalline solids. So these are solids where the components that they're made up of, atoms, molecules, or ions, depending on the type of substance that it is, those components are arranged in a highly regular and periodic fashion. Okay, so that's what crystalline solids are. So in a crystalline solid, we can very carefully define the distances between those repeating units, the atoms or molecules or ions that make them up, how exactly they're arranged in three dimensions, the spacing between them. All those things can be very well clearly defined when you have a crystalline solid. And then what sort of defines the structure of a crystalline solid is a more, I guess, abstract parameter called a lattice, or a more abstract entity called a lattice, which is, this is the three-dimensional system of points that you can use to define a crystalline solid, where each point represents an atom, a molecule, or an ion in the crystal. Okay, and so the lattice is sort of this infinitely repeating pattern of points that goes in all directions to make up that crystalline solid. We're going to only talk about three-dimensional lattices in here. There are also two-dimensional lattices, which in some ways are easier to visualize, I suppose. And there's some chemical compounds that you can kind of think of as a two-dimensional lattice, but most things in real life, of course, are three-dimensional. I'm trying to see if there's anything in this room that would classify as a lattice. I don't think we really have. The carpet here is a very random pattern, it seems. So I can't really easily describe that as a lattice. But imagine you had like a tile floor where you have squares, and those squares are repeating in two dimensions over the whole floor. You could describe that as a lattice, where it's a regular repeating array of points that are going in all directions. That case, two-dimensional. The types we're going to talk about for chemical compounds are three-dimensional, where they make up regular shapes by virtue of having this repeating pattern that goes in all three directions. So then what we call then, another term that's important to understand how we're going to sort of describe these different crystalline solids is via what's called the unit cell. So the unit cell is the smallest repeating unit in a crystal. Most of the unit cells we're going to talk about are cubic in shape. So they're cubes that have various parts of their interior volume occupied by atoms or ions. And when we generate a lattice, then we're going to take that unit cell and translate it in all three directions. Basically, just stack it together in all three directions. Okay, so as an analogy to that, you can think about it like stacking blocks. As I said, the unit cells we're going to talk about here are almost exclusively cubic in their shape. So they're just cubes with different atoms or ions arranged inside of them. And so it's then to generate a lattice from those cubic unit cells, you would take those cubes and just stack them in all three directions, just like you're stacking blocks, for example. And that whole array of blocks would then be called the lattice, where each little block in there is a unit cell, and you're stacking those in all three directions to arrange them into a lattice. So that's how we typically, in chemistry, define these different structure types, is via the unit cell, a description of what shape the unit cell is. And if you want to get more quantitative about it, which is sometimes useful to do, although not so much in this course, you can describe how long the edges are on the cube, how far apart the atoms are, and things like that. So we're going to describe things mostly qualitatively, I suppose, but we're going to talk about unit cells in the context of both metallic solids, metals from the periodic table, as well as ionic solids, which is the last topic we'll cover next week. All right, so let's talk then within crystalline solids. There's different classes as well that are a function of what type of substance it is. So all of these are crystalline solids, but there's different compositions of them that define, from a chemistry standpoint, what they would be as well. So one type is an atomic solid. So an atomic solid is just made up of one type of atom, so it's an element. So a crystalline solid that is an element in terms of what it's composed of would be defined as an atomic solid. So examples of atomic solids include diamond, which is a crystalline form of elemental carbon, and most metals. We're going to talk a lot about metallic structures today that fall into this category as well. So most metals on the periodic table exist as solids, and often they're in crystalline form, and they would be classified then as an atomic solid because they're just made up of metal atoms arranged in a regular pattern. All right, another type that, as I said, we'll talk about next time is ionic solids. So basically, any crystalline ionic compound would be an ionic solid. That's fairly obvious to identify. So these are made up of a regular pattern of positive and negative ions that make up the lattice points. And pretty much any ionic compound you can think of, if it's in this crystalline form, which they usually are as a solid, would fall into this category. So you've probably seen crystalline sodium chloride, table salt, little nice cubic colorless crystals. That's a crystalline ionic solid, and many others that we're going to talk about as well. So we're going to focus just on a few structure types. As we said, with most things in chapter 9, we're going to cover a lot of things, but not a lot of depth. And that's going to be true for these structures as well. So for ionic solids, we're going to focus on binary ionic compounds, relatively simple formulas, and just a few classifications of those structures that they fall into. But that's not till next time, as I said. And then the one that we won't really cover in a lot of detail in terms of its structural aspects, but we should be familiar with what it is, and we'll talk a little bit about their properties as well, are molecular solids. So molecular solids are covalent compounds or I guess you could put polyatomic elements in this category as well. Those would be the elements like I2 that are made up of two atoms bonding together into molecules, or S8, P4, those ones that we talked about, where you have a bunch of molecules now that are packed into a solid. So in this case, the lattice points are the molecules, and they're going to be held together by intermolecular forces. We're not, as I said, we're not going to describe the structures of these in a lot of detail, but we're going to talk about them just a little bit in terms of what they are and what their properties are. So an easy example of this is ice, the solid form of water, which, as you likely are aware, can form a crystalline array where it's shown up here, water molecules packed into these regular sort of hexagonal patterns, okay? So that's molecular solids. Today we're going to cover a few types of atomic solids primarily, especially the metallic ones is going to be the focus of our efforts today. So let's get into that. So the first thing we have to cover before we talk a lot of detail about the structures of metals is how are metal atoms held together in the solid phase. And what ends up happening is when metal atoms are held together in the solid phase, we might think like, well, what are the forces that hold them together? You know, they're just single atoms. How do they sort of arrange themselves and get locked in place in those solid forms? And what's responsible for that is a type of electronic structure called metallic bonding. So this is a bit different than what we've seen before. We've talked about a lot of different types of bonds. I mean, not a lot, but I guess we've talked about ionic bonds and covalent bonds, and we talked about, especially covalent bonds, a lot of details about how they form, the sharing of electrons, the orbitals that are involved, all that stuff. The key thing with covalent bonds that we talked about is that they're primarily going to be either localized between two atoms or maybe delocalized over a small segment, like in benzene or some of those other delocalized structures we described at a low level of detail. But with metallic bonding, things are a little bit different. You have what's called, to describe the bonding of metal atoms in crystalline solids, you have what's called the electron C model. Now, this is hard to draw or describe, I suppose, but we'll do our best. And what happens in this is you can sort of think about it as in metals, they're all the way on the left side of the periodic table. And as we described much earlier in the course, they have pretty low ionization energies as a result because their outer electrons are not held very tightly. So they have 1 or 2 electrons in their valence shell. They're not held very tightly. They're easy to ionize, all those things. So what happens in a metallic solid, let's say we're in the first column of the periodic table, group 1A, those metals all have that 1 valence electron that's located in the S subshell that's furthest away from the nucleus. And so that 1s or 2s or 3s, whatever the electron is that's in that subshell, is going to be loosely held from the nucleus. And so you can kind of think about this then as an array of positive cations where all the core electrons would be sort of held in place within those cations. But then what you have, and this is where you have to just sort of draw it in a very non-specific way, is all of the valence electrons, 1 from each atom, are going to be loosely held and sort of just floating around the structure and holding everything together. That's why it's called an electron C. You don't have electrons, those valence electrons are not localized between a pair of atoms. They're kind of just floating around the whole structure. So you kind of just draw it as like a smear of electron density that covers the whole structure. So the valence electrons are loosely held. So that's what this is showing. This yellow smear that I'm drawing very non-specifically is what's called the sea of electrons, meaning that they have loosely held valence electrons that are able to just float around the whole structure. So in metals, all valence electrons are loosely held and delocalized. And that's responsible then for holding all of those nuclei together in these regular crystalline solids. These electrons just sort of floating around and kind of acting like a glue that holds everything together. So just as a quick extension then, if we go to group 2A on the periodic table, the second column, those metals have 2 loosely held valence electrons. They're all S2 valence configurations. So starting with magnesium, calcium, strontium, barium, and so on, that whole column, they're all 2 loosely held valence electrons. And so you can kind of formulate it then as a bunch of 2+ cations with all the core electrons in place. And again, these structures are 3-dimensional, but I'm just drawing sort of a flat plane of them to sort of illustrate the concept. But you have these loosely held, now 2 valence electrons per metal, but still loosely held and floating around the structure in the same way. Okay. So that's what we mean by the electron C model. You don't have clear localization of the valence electrons in metals. They're able to delocalize over the entire structure and float around quite freely because of the nature of those valence electrons. So then when we talk about properties of metals. So how do the properties of the metals determined by this sort of bonding model and by the arrangement that they have? So if we talk about the melting points of metals, they tend to be moderate to high. Again, we're going to mostly describe things qualitatively in this chapter, but most metals have moderate to high melting points. We said all of them except for mercury are solids at room temperature, and most of them you have to go to at least fairly elevated temperatures to melt them. Now let's see what happens as to the melting point in general as we go across a period or down a group. So across a period, we're primarily talking about going from group 1 to group 2. Some of the predictions and properties don't work as well in the transition metal series, but if we're talking about just the main group metals, group 1 and group 2, those first two columns, as we go left to right, we would expect the melting point to increase. And that's because of the picture that I drew on the previous slide, which is that in group 2, you have a higher charge delocalized. So you have 2 valence electrons that are delocalized and 4 2+ cations at each lattice position. So that leads to stronger attractions between those metals, making it harder to break those attractions and liquefy. Okay, so in group 2, you just have more delocalized valence electrons, so there's a stronger force of attraction holding everything together. So when you compare 2 elements that are next to each other in the periodic table, like sodium and magnesium, group 1 and group 2, you would expect the group 2,1 magnesium to have the higher melting point for that reason. Now, as we go down a group, which is down a column of the periodic table, so they all have the same valence electrons in that case, but in that direction, the melting point would decrease. And this also relates to things we've talked about in the past, which is that as you move down a group of the periodic table, the radius increases. So you'd have larger metal ions as you go down, and that leads to a weaker attraction to the electron C. Basically, that charge is more spread out and not held as tightly by the nucleus, which is further away from that valence C of electrons. Okay. So as you go from lithium, sodium, potassium, rubidium, cesium down that column of the periodic table, the melting points progressively decrease as the metal ions get larger and larger, and they're going to be held then less tightly then. So lithium is a pretty relatively high melting solid. Cesium is still a solid at room temperature. I forget the exact melting point, but you don't have to go very high to melt cesium. Just a little bit above room temperature will melt it. Now that's the melting point of electrons, which is moderate to high. It's relatively easy to melt metals. Again, you don't usually have to go to ridiculous temperatures to melt a metal. And that's because, those atoms are held together by that electron C in sort of these regular structures. But if you melt the substance into a liquid, those valence electrons are still in contact with all the formally positively charged ions. So you're disrupting that network a little bit to melt it, but in the liquid phase, they're all still in contact with each other. So you don't really break the metallic bonding to do that altogether. And that's, as an example of that, mercury, which is the only metal that exists as a liquid at room temperature, still retains many of the properties of metals that we're familiar with. It's still shiny in color. It still conducts electricity very well. We'll talk about those in a little bit. And so melting a metal doesn't completely disrupt the metallic bonding. So it requires some energy to do that, but you're not totally breaking everything apart. But if you want to boil a substance, as we talked about in other contexts, you have to break all of the forces that are holding the atoms or molecules together and get them to go into the gas phase. And so for metals, then they have very high boiling points. It's not particularly easy to boil metals because it's difficult for those metal cations that are held together by the valence electrons. It's difficult for those to break away from one another. There's still a lot of forces holding them together in the liquid phase, and you have to disrupt all of those forces to be able to atomize or boil substance. Okay, so long story short, metals have moderate to high melting points. We should be a little bit aware of how they change across the periodic table for those first two columns especially. but their boiling points are very high because that requires you to break all those metallic bonds completely. So that relates to their phase changes. Now let's talk a little bit about the physical properties of metals themselves that, again, derive from this electron C model and the ways that these atoms are held together. So the first is if we talk about mechanical properties. Mechanical properties is essentially the response of a material to an applied force. So if you put a force on a material, how does it behave? And the key distinction of metals relative to many other substances is that they're what are called malleable, which is just a fancy way to say that they're bendable. So most metals have pretty flexible structures. You can bend them, you can stretch them, you can pull them into wires, all that things that we're probably familiar with already at a basic level. And that's because when you have this electron C model, even though there is a regular pattern that they would form as a crystalline solid, they're not held that tightly in place because the electrons are delocalized. There's not a real electronic structure to it. So you can kind of slide those atoms around, move them around a little bit without completely disrupting that metallic bonding. So these metal ions can kind of slide through the others and slide through the electron C and change their shape pretty easily. And there's of course a limit to that. You can still, of course, you can break a paper clip, right? If you pull on it hard enough, it'll break. But you can bend it to some extent without completely disrupting those metallic bonds. And you can think of it as just the ions are sliding through that electron C and able to then change their shape as a result. And the big one for metals that we're also likely familiar with is their electrical and thermal conductivity. And especially electrical conductivity should make sense now from what we've talked about, which is that metals are good conductors because those electrons are loosely held and freely flowing through the material. When you want to conduct electricity, I should say the good conductors, when you want to conduct electricity, you need electrons to flow freely through the substance. And in metals, those valence electrons are perfectly arranged to do that with low barrier to their transport. So in the solid or liquid state, you have those loosely held delocalized electrons. And so those mobile electrons allow charge to be passed. I suppose it's less obvious why that makes them good thermal conductors, and that's beyond the scope of this course, but they are also good thermal conductors, meaning that heat transfers well through metals as well. Electricity should be the obvious one from what we talked about. You have these loosely held, freely moving valence electrons, and so they can conduct electricity rather well. And that's a fairly unique property of metals. There's not many other classes of substances that can be designed to be perfectly conductive. There's exceptions to that, but in most cases, most of the conductive substances that we deal with in everyday life are metals for that reason. All right, so that's some of the properties of metals that we wanted to talk about. Any quick questions on those? All right, the big thing which does present a little bit of a barrier to learning because it's quite a bit different than what we've done before, but as I said, we're not going to get a lot of depth on this topic. We're going to just introduce it, is describing the structures of crystalline solids. And we're going to start with metallic solids, the type that we're describing now, before moving on to ionic solids. And like I said, it's just some terminology and some concepts that we haven't seen before, but I think in the end it's not too bad what we expect you to internalize. So the first thing I want to describe, though, is how do we determine the structure of crystalline solids? Now, this is mostly background material that we're not going to really test you on any level of detail, but if you're curious, or it just kind of hopefully sets the stage a little bit, how do we know how the atoms in a metal are arranged? Atoms are very tiny, of course. We can't see them. We can't just hold up a magnifying glass and say, oh, there's the atoms arranged in a row. There they are. How do we actually do that? We do that with a technique called X-ray diffraction, which is where, if you're familiar with the concept of diffraction in general, that's when you have electromagnetic radiation. If it hits a regular array of points, what we often call a diffraction grating, if it's sort of in a macroscopic phase, that electromagnetic radiation will spread out and diffract in all directions. And X-rays do the same thing because they're a form of electromagnetic radiation. And that diffraction occurs when the spacing between the points is similar to the wavelength of the electromagnetic radiation. So X-rays have wavelengths that are usually the type that you use for this experiment are on the order of like 1 angstrom, 10 to the minus 10th meters. And that's approximately on that same order of magnitude how far apart atoms are in crystals. So the atoms are the points of these diffraction gratings that are regularly arranged. They're about the right distance apart. And so when X-rays hit these regular arrays of atoms, they diffract in all directions, okay? So that's basically the experiment. It's a scattering experiment where X-rays are going to scatter off of atoms in crystals, where those regular repeating atoms can be thought of as a diffraction grating at some level. Now, when that happens, there's two possibilities. So your primary X-ray beam, and this is what's sort of shown here, your primary X-ray beam strikes the crystal, and then because of the interaction with the atoms in the crystal, they diffract in a bunch of different directions. But there's two possibilities when that happens. The diffracted X-ray beams can align constructively with each other, where you get an amplification of the X-rays in that specific direction. So that's called constructive interference. And then they can also align out of phase with each other. So they can diffract in a way that the X-rays that come in that direction are out of phase with each other. And they destructively interferes, which basically cancels them and you lose the intensity in that direction. So in an X-ray diffraction experiment, you're going to be measuring where that constructive interference occurs, because at those specific directions and angles, you're going to have X-rays coming off the crystal that have reinforced intensity, and then they're going to strike a photographic plate, or now we have fancier detectors that are reusable, that are electronic in nature. And those diffracted X-rays are going to hit your detector, and you're going to get a spot that tells you in each of the orientations that those constructive interferences occurred. So that's what those spots are that we're showing here in this picture. So the spots represent the places where that constructive interference occurs. So this experiment then requires you to do this in a bunch of orientations. So you rotate the crystal in all directions relative to the X-ray beam, measure this pattern of constructive interference, and then from there, there's a lot of math that goes into determining what the structure of the solid is. So that, of course, that's beyond the scope of a general chemistry class. So we're going to skip a lot of the important details. It is interesting to see sort of the progress of this technique, though, because when this was first done, let's say I think probably around 100 years ago or so was when this was discovered and people were starting using it. You had to do this very manually. You had to rotate the crystal manually, and you had to replace the photographic plate in each orientation. So you'd have to collect all these different photographic plates. Then you have to manually measure where all the spots are, do all the number crunching on pen and paper. And it took probably a few years on average to get one crystal structure worked out from this. It was a lengthy process at that time. These days, we have computerized instruments that rotate the crystal automatically. You don't have to replace photographic plates. You have electronic detectors that measure it and refresh themselves naturally. And with a good crystal, you can collect the data and determine the structure in an hour or less. And so we have this equipment here at UH to do it, and it's much faster, much easier now. So you don't really need to know the math that well to be able to do it, and it's very automated in a lot of ways. Now, the math that goes into it, we're going to talk about at just a very basic level, is what's called Bragg's Law. Now, Bragg's Law is another one that sort of has an interesting origin story. So Bragg's Law is named after a father and son, Bragg, who won the Nobel Prize for discovering this. So, I played baseball with my dad when I was a kid, but Bragg got a Nobel Prize with his dad when he was a kid. So good for them. A different approach to life, I suppose. He wasn't a kid when he got it, but it was a father and son duo that kind of came up with this together. Now, if you look at how Bragg's Law works, basically what you're measuring is the angle at which the X-rays are diffracting. So that's your angle theta here. So it's kind of like a reflection process. It goes in at some angle, emerges at the same angle. Another parameter that goes into this is lambda, which is the wavelength of the X-rays. So that's the parameter that goes into this. Theta, as we said, is the angle of incidence, the angle relative to the plane of atoms that the X-ray is striking. And then another important parameter here is you're measuring, what this ultimately is going to give you is the distance between layers of atoms. We'll talk about it a little bit, but we should appreciate the idea that if you form a three-dimensional lattice, a regular array of points, you can sort of cut that up into a bunch of repeating layers that are stacked on top of each other. So these layers are going to have a specific distance between them, d. And again, these layers are planes of atoms. And that's really what the output is going to be then. You're going to use Bragg's law to figure out what is the distance between planes of atoms, equivalent planes. You do that in many different orientations as you rotate the crystal around. And with all that information, you can piece together the three-dimensional structure. And there's a lot of complicated math that goes into that we're not going to cover. But the Bragg equation, which we won't really ask you to use, but we want you to be a little bit familiar with in terms of just how this technique works, is given as such, where n lambda equals 2d sine theta, where n is some integer value. So you can get first order diffraction when n is 1, second order, and so on. But all the measured outputs from these experiments, when you know the wavelength of the X-ray that's going in, and you know the angle that they're being measured, that's what comes out from that output. You measure the photographic plate, you can determine the angle with which that spot hit the plate from the crystal, and you can back out the distance between the planes from that equation, and that allows you to piece together the structure. So again, don't worry about the details of that too much. We just want to introduce how do we get this information to begin with. The important part is to understand what the information is that we get from this, and then how we classify the structures on the basis of that. So the first thing we need to understand is we're going to be dealing primarily with cubic structures, where the unit cell can be described as a regular cube, 3 identical sides, all 90-degree angles. And when you have a cubic unit cell, you can have atoms that are arranged in different ways within that unit cell. Different positions in the cube that the atom can be placed for that structure. And so one of those would be to put the atom at the center of the cube, somewhere enclosed entirely by the cube, not necessarily directly in the middle, but somewhere inside the cube. Is what's called a body center position. So if it's right at the center, it's body center, but anything that's in the interior of the cube would sort of count. And an important thing then to understand is some of the properties of these substances we're going to talk about that relate to their structure requires to count how many atoms are there in each unit cell, and especially for ionic compounds, how many of each type are there to be able to balance the formula correctly. So if you have an atom that's completely inside the unit cell, it's not going to be shared with any other unit cells. It's completely enclosed. And so an atom that's in the body center will count as one full atom inside of that unit cell. Right? So counting atoms in unit cells is one of the things we expect you to be able to do. So if we describe an atom as being in a body center position, it counts as an entire atom for that unit cell. Now, other possibilities emerge, though. And so one of those would be to put the atom directly in the center of one of the square faces of a cube. There's 6 square faces in a cube, 4 around the outside, 1 on the top, 1 on the bottom. And if an atom is arranged directly on that face center position, that's what we call it, face center. In terms of how we count it, then, we should recognize that if we stack these unit cells in all directions, this face center position, this atom that's located there, is going to be shared by 2 neighboring unit cells. Because when you stack cubes together, you put 2 faces together, one from each cube. And so the atom that's located there is going to half belong to one cube, half belong to the cube that's next to it. So face center atoms are shared by 2 unit cells when you generate the lattice. So each face center atom is going to count as 1/2 for that one specific unit cell. All right. Now you're going to typically have more than one face occupied, so you're not going to have half atoms in the structure, obviously, but you'd count each of the face centers that's occupied as half of an atom. Counting is going to be, as I said, a little bit more important for ionic compounds, but we'll talk about it a little bit for metals as well. Another position in a cubic unit cell is an edge position. And so a cube has 12 edges. This is one of them shown here. You have the 4 others, 3 others around the side, 4 on the top, 4 on the bottom. So 12 edges in a cube that can have atoms occupied. If you visualize stacking together cubes in all 3 directions, the edge positions are going to be shared by 4 different cubes. So think about stacking blocks. Each edge is going to be at an intersection of 4 of those blocks. So the edge positions are shared by 4 unit cells, and as a result, they count as 1/4 of an atom for that cell. Count as 1/4. And then the last possible position we can put is the corner of the cube. Now this is pretty much always going to be occupied, as it turns out, but it's the last one we're covering because it's probably the one that's hardest to visualize. But this is going to be, if you think about the corner of a cube, you have to, if you have cubic blocks at home or you have small children in your life that you can share with, you can verify this for yourself. But each corner position is going to be shared by 8 cubes. You're going to have the 4 that are in the same level as that one, and the 4 that are on top of that as well are going to be occupying that same corner. So there's going to be 8 unit cells that would share each corner when you stack them in all 3 directions. So each corner atom then counts as an 1/8 for 1 unit cell. All right, so that's one of the things that we expect you to be able to rationalize and talk about a little bit, and also then be able to, when we describe these structures, it's going to be a little bit helpful too for defining some of the things. So we're going to talk about 3 different cubic unit cell structures that all of them have the same shape. They're all a cube, but in terms of they're just different ways that the atoms are arranged inside of that cube. Right? And so what we're going to do is first talk about the easiest of those, as the name might suggest, which is the simple cubic structure. So for some of these structures, it's helpful to think about how we generate them for a layer of atoms. So we start with 2-dimensional layers, then we can stack those layers to generate these 3-dimensional structures. So this is how it works for simple cubic. You start with a layer of atoms. Now all the atoms are touching one another. They're as close together as possible, except that each layer is sort of eclipsed on top of the other one. So it's a row of atoms, and then directly below that is another row of atoms. You're not slipping the layers at all. They're just stacked in this way. And then you take one of these layers and you just stack it on top of each other. And then what will happen is the smallest that you can draw in there that is going to be repeated just by translation only is going to be a cube that has 1 atom on each corner. So this would be 4 atoms from one layer. This would be 4 atoms from the layer below it, and that's going to go on in all directions. So the unit cell is described then as a cube, and that's going to be generated by stacking the layers directly on top of one another. For this structure, I would say understanding the layering is not that important. For 2 of the other structure types we're going to talk about, we kind of classify them on the basis of how the layers are stacked. So it's a little bit more useful. But this is how it's going to be generated for the simple cubic structure. The important thing to recognize is that what happens then is for that cubic unit cell, all you have is just 1 atom in each corner. You can draw it like this to sort of more clearly show the arrangement. In reality, the atoms are close together as they can be. They're touching one another. And so it kind of looks like this, where each corner has an atom that's neighboring the other ones that are in the same layer and the one below it. Okay? Now, what we're also going to go through are some derivations in terms of some information about the length of a side, the volume of the cube, and importantly at the end, what's called the packing efficiency. Now, these types of derivations, you're not going to be like that responsible for reproducing all of them, but I think if you understand where a lot of this stuff comes from, it does help you to sort of visualize these structures at a deeper level. So if you have a simple cubic structure, if we go back up here, if you look at one face of this cube, you have atoms in each corner that are touching along each side, and so you can kind of draw it like this. All right. So in cubic unit cells, the length of a side is abbreviated as lowercase a. So that's going to be the length from one corner to the other along the side. If you have a unit cell, we're not going to talk about this. If you have a unit cell that has 3 different side lengths, you would call it A, B, and C, but cubes all have the same side length in all directions, so it's just called A. Is the only side length you need. And then along this side length, we have one atomic radius that takes us to the center, and then the second one that's, so what this works out to then is the side length A is equal to 2 times the radius, where R is the radius of the atom that's making up that structure. Okay. So if we want to talk then about the volume of the unit cell, the volume of a cube is A cubed, if you remember high school geometry. In this case, that's 2R cubed or 8R cubed. Now, an important thing for us to be able to do for all these structure types is count how many atoms or how many spheres more generically are in that unit cell. So as we talked about last time, we have to look at where the atoms are. And the simple cubic structure, going back here, is probably easier. As I said, all 8 corners are occupied. And as we previously described, the corners are each shared by 8 unit cells, so each of those counts as 1/8. So in total, what we have is 8 corners occupied. Each of them counts as 1/8 of an atom for that unit cell. So in total, there's just 1 atom per unit cell in a cubic unit cell, simple cubic unit cell. 8 1/8 is a total of 1. Okay, so the total of 1 atom per unit cell. And that means then the volume of those atoms, the volume of the spheres that are inside the unit cell, there's 1 atom, and each atom has a volume of 4/3 pi r cubed, more geometry. So it's just 4/3 pi r cubed is the volume that's occupied by those spheres. So then what that finally leads us to, which is a good way to sort of classify and differentiate the different structure types, is what's called packing efficiency. Packing efficiency is defined as the volume of the spheres or the atoms that are in the unit cell divided by the total volume of the cell, which is the volume of the cube, multiplied by 100. So in this structure here, we found that the spheres occupy a total volume of 4/3 pi r cubed, a total of 1 sphere in the unit cell with that volume. And then the volume of the cube itself can be expressed as 8r cubed. 2r is the side length, cube that. So 8r cubed, which equals, if you simplify it down, pi over 6 multiplied by 100. 52.4%. All right. I guess the relative numbers are more important than the exact numbers, but that's what we get for simple cubic. 52% of the cube's volume is occupied by the atoms that are in that unit cell. Not particularly efficient, as we'll see, but that's one way to arrange atoms is in a simple cubic structure, and you end up with this packing efficiency. All right. Any questions so far? All right. The next major structure type is called body-centered cubic. And so the way that we generate this from layers is we place the atoms in a 2-dimensional layer, but with a space in between them at first. So they're regularly arranged. The rows are still directly eclipsed on top of each other, but there's a space in between each of them now, as opposed to what we did before. Then what you do is you take a second layer. Now I'm showing the second layer in red so you can visualize it more easily. It's still the same atom. If we're talking about a metallic structure, it's just one type of atom that makes up every lattice point. So the red atoms are the same as blue. We're just using color to distinguish them a little bit. And you're going to take an identical layer of atoms, but you're going to place it over the gaps in the first layer. So that's what these red atoms are doing. They're sitting, it's the same type of layer, but it's sitting on top of the gaps of the second layer, of the first layer. So the second layer goes over the gaps that are in the first layer. And then you're going to just repeat that process where the third layer is going to go over top exactly where the first layer was. So it's just an alternating stacking. What you might call A-B stacking is one way to describe it. You stack a layer, you stagger the second layer, and then the third layer goes back to where you started. So I'm showing that again in blue to indicate that that third layer is now eclipsed with the first layer. Now, again, if you don't fully follow the stacking aspect of this, your performance on the exams should not suffer too much, because what we mostly expect you to know is how does that then result in terms of the arrangement of the atoms in one cubic unit cell. Now, as the name suggests for body-centered cubic, what you end up having is a cube where you have atoms on each corner of the cube, and you have one directly in the middle. So simple cubic, we only had atoms on the corners. Body-centered cubic also puts one directly in the middle of the cube. So that's shown here. This is the more space-filling diagram shown down here. This is what the lattice would look like, which is more complicated in this case. But again, I'm going to focus primarily on this picture or this picture here to help us understand it. So body-centered cubic results in one atom on each cube, one atom directly in the center. All right, so then we go to some of those same levels of analysis about the body-centered cubic structure and how that relates then to get us to the packing efficiency. Now, this one is a bit more complicated, because if you look at one side of the unit cell, the atoms along the sides are no longer touching. They have that little bit of a gap in between them, which we said is how these layers are generated in the first place. So if you just go along the side length here, you can't really define that in terms of the atomic radius, because the two radii are not touching along that side. There's a small gap in between them that you also have to account for. So the way that we can then define the dimensions in this structure is to actually start at one corner of the cubic cell and go three-dimensionally completely to the opposite corner. So here I'm starting at the back left, ending up at the front right. As we go through one of those cube diagonals, you go through the radius of the atom that's in the corner that you're starting in. You go through the entire diameter of the center atom, and then you come out by going through the radius of the top one. Now, it's hard for me to draw that because the line would actually end up being behind this front atom there, but you can try to do a little bit better. Let's try it like this. So you're going to go through there and then through there. And as you go through that diagonal, you're going to go through the radius of this cube, of this sphere, the whole diameter of the center, and then the radius of the one on the opposite corner. And that's what this is showing here. And this is sort of a two-dimensional slice, a two-dimensional slice of that, where this is the length of one side, and then this here is going to be the this is going to be the cube diagonal shown in red here. Okay, so from geometry, then this, if we call this distance here the diagonal d, that's going to be d squared is equal to a squared plus a squared plus a squared. That's again just geometry. We don't expect you necessarily to know that. And then so the distance, this diagonal is going to be given as a radical 3. So this is side length A, this is a radical 2, and then the diagonal here is a radical 3. So then if we want to define the length of a side in terms of the radius r, we know that the diagonal is equal to a times the square root of 3. And as we said earlier, that requires you to traverse through 4 times the atomic radius. The radius of the first corner atom, the whole diameter of the center, and then the radius of the opposite corner. So that diagonal is equal to a radical 3, and it's also equal to 4 times the atomic radius. So in this structure here, the side length A in terms of atomic radius is 4r over radical 3. So again, a bit more complicated with body-centered cubic. So that part's a little bit hard to come up with, I'll give you that. But now we can do the counting that we should already know how to do, which is looking at which positions in the cube are occupied. So in body-centered cubic, you still have all 8 corners occupied. So 8 corners, each atom counts as an eighth because it's shared by 8 unit cells. And you also have one atom that's completely in the center of the unit cell. So that will be classified as a body-centered position, completely enclosed by the unit cell, not shared by any other neighboring cell. So that one body-center atom counts as a full atom for that unit cell. So in total, there's now 2 atoms per unit cell, or 2 spheres per unit cell, if you're describing it in non-chemical terms. 2 spheres per unit cell when you have a body-centered cubic structure. a total of 1 from the corners and the additional one that's stuffed in the center there. All right. And so then that means the volume of those spheres is now, there's 2 atoms in the unit cell. Each one has a volume of 4/3 pi r cubed, which is 8/3 pi r cubed. All right. So this one has the most complicated geometry to get to this point, especially this first part here. But once we have that information, we can calculate the packing efficiency in the same way. 8/3 times pi r cubed is the volume of the spheres. This value cubed, 4r over radical 3, is the volume of the cube. So they're both in terms of radius now, so the radiuses cancel out. And what we end up with is 8/3 pi over 4 square root of 3 cubed times 100. I'm not going to try to simplify that any further, but just write it as a number, which is 68.0%. All right, so the packing efficiency is much higher. It was 52% for simple cubic. We stuffed another atom in the center, and now 68% of the cube's volume is occupied by the atoms in the unit cell. And again, those relative numbers especially are the more important ones, so we should recognize at this point that the body-centered cubic structure has more efficient packing than the face-centered than the simple cubic structure. All right, any questions on that one? So now the question is there any other way to do this even more efficiently than 68%? And I probably would not have asked that question if the answer was no. So the answer is, of course, yes, which is what's called the face-centered cubic structure. Now, this one is probably the most complicated in terms of the layering. We're going to still describe it a little bit just because it's, I think, useful to think about, and it distinguishes it from one other structure type we're going to also describe. This is our last cubic structure, as it turns out. And so face-centered cubic is also sometimes called cubic closest packed, CCP, not Chinese Communist Party, but cubic closest packed, face-centered cubic. And it's called that because it is the most efficient way that we can arrange atoms into a cube, as it turns out. And I'll give you the numbers at the end, of course, just to verify that. But this is what happens. And so the way that we generate this is, the key difference here is now we're starting, each layer is what's called a closest packed layers, or close packed layer of spheres. So if you look closely at the difference here, there's no gaps between the spheres in this layer. And the second row of atoms is staggered relative to the first. So you have little gaps in the first row that you're sort of filling in as best you can with the second row. So this is called a close packed layer. This is the closest together that you can put spheres into a two-dimensional layer. And to try to distinguish it from before, if we go all the way back up to here, we saw that in this one, the rows were directly on top of each other, and there were these reasonably large spaces between them. In this one, we intentionally built in even larger spaces to be able to fit an atom in there. In the close packed structures, each layer of atom, the spheres are as close together as they can possibly be. You've closed those gaps as much as possible. Okay, so you start with that. And so then what you do is you stack those layers in a very particular way. So down here, the diagram that we're going to use to describe this, the first layer is going to be in yellow, and we're going to call that the A layer. The second layer, which is shown here as hollow circles, is going to be on top of the little triangular gaps in the first layer. So each layer of atoms has these little triangular gaps between the spheres. There's always going to be a little bit of a gap between spheres when you stack them. And you're going to put the second closest packed layer directly on top of that, where those little triangles are. So we're going to call that the B layer, shown in blue. And then the third layer, which is shown in green, is going to go on top of the triangles from the second layer. So you're still not going to be repeating yourself yet. We're going to still stagger it one more time. And so the C layer is going to be in green, and that results then in this sort of stacking pattern, where yellow is A, blue is B, green is C, and then yellow is A again. And that's when you start repeating yourself. So it's sort of a staggering of 3 layers before you repeat the pattern over and over again. So what we refer to this then is we call it ABC, or sometimes ABCA packing, indicating that you're going to stagger the layers 3 times before repeating yourself and eclipsing the layers. So the 2 yellow layers are eclipsed, but the 2 layers in between are both staggered relative to each other. So we call it ABC packing. Now, it's very hard to visualize, I'll admit. How do we get from this packing of layers into a cubic structure? What you have to end up doing is you sort of have to turn the whole thing on its side, because this direction here that's perpendicular to the layers is actually the diagonal of a cube. So you'll notice that in this cube here, the yellow ones, which are the two A layers, are on opposite corners. They're not stacked straight up through the cube like that. It's sort of through the diagonal. So it's hard to maybe make that visual transformation, but what this results in then, and that you should be able to recognize and describe, is a structure that looks like this, where what you have is one atom in each corner. So all of the cubic structures have the corners occupied. There's no exception to that. But then in addition to the corner atoms, you have one atom on each face. Maybe a little bit hard to see here with all the blue lines, but if you go down to this one here, you can clearly see that. Corner atoms, and then one atom in each of the 6 faces. 2 of them clearly shown there, 1 of them clearly shown on the top, plus 1 on the bottom, 2 on the back faces that you can't really see. So there's 6 faces in a cube. Each of them has an atom directly in the center of that face in the face-centered cubic structure. I mean, the name kind of gives it away, I suppose, but that's what results in it. You should be aware of this ABC packing as a way to describe it. If you don't fully visualize the relationship, that's okay. It's hard to do. But once you get to this cubic structure, you should be able to describe it well with one atom in each corner, one atom on each face. Okay? So if we go through then the same analysis on this one, length of a face diagonal, length of a side, and so on. If we go here, this is going to be the face of our cube. So it's a little bit simpler than the last one geometrically, as it turns out. So as we go through one face of the cube, we go through the radius of an atom in one corner. We go through the whole diameter of the face-centered atom. And then to get to the opposite corner, we go again through the radius of the atom that's in the opposite corner. So in this case, the side lengths here are A. And we're talking about now the diagonal of a side. The diagonal of a squared, A squared plus A squared equals D squared. So the diagonal length in this case for a, let me do it in red. This length here is equal to A square root of 2. And that's the geometry part of it that we're not going to hold you to too much. But D is equal to A radical 2, the diagonal of a face now we're talking about. And then the length of a side, we can just relate the two. So the diagonal A square root of 2 is, as we said, equal to 4 times the radius. So that means A is equal to 4r over square root of 2, or more simply written as 2 square root of 2r. Okay, so that's now the relationship between the side length and the radius of the atom. Counting the spheres, this again is probably the most important part you should know how to do. We look at the structure, and as we said, there's all 8 corners occupied. That's going to be true for any of the cubic structures. And now we have all 6 faces occupied as well. As we said, when you stack cubes into a lattice, 2 of the faces will touch each other from neighboring unit cells, so each face counts as a half. So all 6 faces have an atom on it. Each of those is going to count as 1/2 of an atom per unit cell. So in total, there's 4 atoms per unit cell in face-centered cubic. 1 again from the corners, but now 3 additional ones that come from the face positions. So the volume of those spheres is now 4 atoms times 4/3 pi r cubed for each atom. R again is the radius of the atom. 16/3 pi r cubed. And again, I'll just do it numerically this time, not go through the effort of simplifying. But for the packing efficiency, we have the volume of those atoms or spheres is 16/3 pi r cubed. The volume of the square, the volume of the cube, A square root of 2r, or sorry, 2 square root of 2r is the side length A. You cube that to get the volume. And so when you cancel out the radius terms and simplify that numerically, you get 74%. All right, so the highest one yet. 52% for simple cubic, 68 for body-centered cubic, now 74 for a close-packed or face-centered cubic. All right, and that's the highest number we'll get, so that's as high as we go. And that's what it ends up with for face-centered cubic. The very last one we'll talk about, but not in very much detail, but just to be aware that it exists, is called hexagonal close packing. And in this case, all you're doing is, instead of A, B, C packing, you're just doing the same type of close packed layers. So it's the same type of layers as we used before, but you're only staggering them twice. So you're generating this structure by doing what's called AB or ABA packing, where you stagger 2 layers before repeating yourself. So it's just a little bit different stacking is all we're doing here. Now, the number of atoms in this unit cell is a little bit more difficult to come up with, I suppose. So we're not going to probably talk about this as much, but the number of atoms for hexagonal. So what you end up having in a hexagonal cell is, if you look at sort of this face of the cell here, which is hexagonal, these atoms here are going to be shared by 6 unit cells, and there's 1 layer on the top, 1 layer at the bottom of the hexagonal. So each of those counts as a 6. We're not going to really hold you responsible for hexagonal packing, but just to show you where this numbers come from. So there's 12 atoms that are in the 2 hexagonal faces at the top and bottom. There's each of those shared by 6 unit cells, as it turns out. You have 3 in the middle from the opposite layer, and then you have the 2 centered ones there that count as a half. Now, hexagonal is a little bit confusing because there's sort of 2 ways to define the unit cell. You can either define it as this actual hexagonal structure or as this sort of smaller piece here. So we don't really have to worry about that too much. So I just gave that to you as for completeness. But the important thing to know about hexagonal, and probably the only thing we expect you to know, are, first of all, the stacking that we use, which is A-B stacking to generate it, and the packing efficiency, which is also 74%. So I'm not going to derive that number for you this time. But it's the same as cubic close packing. So cubic close packing and hexagonal close packing, exact same packing efficiency, just 2 different structures that you can generate by varying how you stack the layers. So that's all we expect you to know about hexagonal. It's there. It's another alternative to close packing structure that's a little bit different, but has the same packing efficiency. The last term we're going to define for you today is called the coordination number. So coordination number is defined as the number of nearest neighbors in a structure. Basically, the number of atoms that's touching another atom in each structure. So it's going to be useful also for ionic compounds we'll talk about later, where it's going to be the number of opposite ions that are around another ion. But in a metallic structure, it's just the number of nearest neighbors, the number of other atoms a single atom is touching in the structure. So thinking about the structures and or the layers they come from, we can kind of come up with the coordination numbers pretty easily. So if we look at the simple cubic structure, if we just look at 1 layer of atoms, and let's just focus on that atom there, how many atoms are touching that one? So you're going to have the 4 that are in the same layer that are touching it, 1, 2, 3, 4, and you're going to have 1 in a layer that's directly above it and 1 in a layer that's directly below it, which I'm not directly showing here. I guess we could kind of see it. So if we do, I'll do a different color than red because that's already shown in red. Let's do like green. So like if we have this atom here, you're going to have 1, 2, 3, 4, and then 1 above, 1 below. So 6 nearest neighbors, 4 in the same layer, 1 above, 1 below. So the coordination number then for this structure would be described as 6. For body center cubic, this one's pretty easy to come up with. Just look at the unit cell itself, focus on the atom that's in the center of the cube, and figure out how many corners are around that center. Well, there's 8 corners in a cube, so the nearest neighbor for that center atom is there's 8 of them. Each corner counts as a nearest neighbor. 5, 6, 7, 8. So the coordination number for body center cubic is 8. And then finally, for both face center cubic or hexagonal, I suppose, but mainly for face center cubic is what we'll do it for. We can count the layers using the layers as well. So if we focus on this atom here, there's going to be 6 atoms in the same layer that are nearest neighbors. And then if we go to the layers that are above and below that, we can look, we'll do that in red. We have 3 in the layer below it that fill up those little triangular gaps that are the same distance away. And then 3 in the layer above it. So again, we're focusing on this atom here. And then we're going to have these 3 as well, 10, 11, 12. So again, whether that fully makes sense or not, there's 6 in the same layer, 3 above, 3 below. Total coordination number for these close packed structures is 12. So the packing efficiency correlates with the coordination number, the number of nearest neighbors. So then just to wrap up quickly, just a quick summary table. This is the important information you need to know. For simple cubic, if you have to go, I'm sorry, I'm going a little bit late, so don't feel bad. But if you could stick around for like 2 minutes, I'll finish this. Primitive cubic is another name for simple cubic. As we saw, there's 1 atom per unit cell with a coordination number of 6, packing efficiency of 52.4%. Body-centered cubic is often abbreviated as BCC, not really a new name, but an abbreviation. 2 atoms per unit cell, coordination number of 8, packing efficiency of 68.0. Face-centered cubic is going to be abbreviated as FCC or sometimes CCP for cubic closest packed. 4 atoms per unit cell, coordination number of 12, packing efficiency of 74. And then hexagonal, which is called hexagonal close packing, HCP. 6 atoms per unit cell, same coordination number, same packing efficiency because it's generated from the same layers as face-centered cubic. So this is the most essential information that you should know, but you should know where some of these numbers come from, especially the counting numbers. And next time we'll talk about how we can translate some of these same insights into ionic structures.